We have reached the speed limit of electricity. To go faster, we are building processors made of trapped light. For the last 70 years, the story of human progress has been written in silicon and told through the movement of electrons. We have shrunk the transistor from the size of a light bulb to the size of a single protein molecule. But we are hitting a wall, a physical, thermal, and undeniable barrier that no amount of engineering can bypass. This is the heat wall. When you push an electron through a copper wire or a silicon channel, it encounters resistance. It bumps into atoms, it vibrates the lattice, and it generates heat. As we pack billions of these pathways into a space no larger than a fingernail, that heat becomes a crisis. Today, our data centers are essentially massive heaters that happen to perform calculations. But what if we stopped using particles with mass and charge to carry our data? What if we swapped the electron for the photon? This is the dawn of photonic computing, a paradigm shift from the electronic age to the optical age. We are no longer just building better computers, we are constructing a glass brain.
To understand why we are moving toward optical chips, we must first understand why the current system is failing. In the world of semiconductor engineering, we have lived by the grace of Moore's law for decades. Every 2 years, we doubled the number of transistors on a chip. But doubling the transistors means doubling the connections. In a modern high-end processor, there are miles of microscopic copper traces. These traces act like pipes. When you send an electrical signal through them, you are physically moving electrons. This creates two massive problems: latency and Joule heating. Joule heating is the energy lost as heat when an electric current passes through a conductor. At the scale of 5 nanometers or 3 nanometers, these wires are so thin that the resistance is staggering. We are spending more energy moving data across the chip than we are actually using to process the data. It is like having a car that burns 90% of its fuel just to get the engine parts moving before the wheels even turn. Then there is the issue of RC delay. In electrical circuits, the combination of resistance and capacitance creates a lag. The signal literally cannot travel faster because the physical medium of copper and silicon limits it. We have tried everything to fix this. We changed the shape of transistors to FinFETs and then to gate-all-around architectures. We introduced exotic materials like hafnium and cobalt. But the physics of the electron remains the same. Electrons are social particles. They interact with each other and their environment through electromagnetic forces. This interaction is exactly what causes the congestion. We are trying to run a marathon in a crowded hallway. If we want to reach the next order of magnitude in performance, specifically for the massive demands of the future of AI, we need a particle that doesn't care about the crowd. We need the photon.
Photons are the fundamental particles of light. Unlike electrons, they have no mass and no electrical charge. In the world of quantum physics, this makes them the ultimate information carriers. Because they have no charge, two photons can pass right through each other without interacting. Imagine two flashlights crossing their beams. The light does not collide or bounce away. It simply passes through. This property allows us to multiplex signals, sending hundreds of different streams of data through the same physical path simultaneously by using different wavelengths or colors of light. This is called wavelength division multiplexing. In a traditional electronic chip, if you want more bandwidth, you need more wires. In an optical chip, you just need more colors. The speed of light is the universal speed limit. While electrons in a wire move at a fraction of that speed due to resistance and scattering, photons in a waveguide travel at nearly 300,000 kilometers per second. But the real magic isn't just speed, it is energy efficiency. Because photons do not experience Joule heating, they can carry information across a chip or across a data center with virtually zero energy loss. We are trading the friction-heavy world of electronics for the frictionless world of photonics. This is why the industry is shifting towards optical chips. We are moving from a world where we move electrons to do work to a world where we manipulate light to represent logic.
So, how do you build a processor out of light? You can't just let light fly around inside a computer case. You have to trap it. In semiconductor engineering, we achieve this through something called a waveguide. Think of a waveguide as a fiber optic cable, but shrunk down to the microscopic level and etched directly onto a silicon wafer. This is the field of silicon photonics.
We use the same manufacturing tools that we use for traditional chips, the same lithography machines, but instead of creating copper wires, we create channels of high-purity glass or silicon. The challenge is how to control the light. In an electronic chip, we have the transistor, a simple switch that turns a current on or off. In an optical chip, we need the equivalent. We use devices called Mach-Zehnder interferometers and ring resonators. These components allow us to split a beam of light, delay one half of it by a tiny fraction of a millimeter, and then recombine them. Depending on how the waves align, they either amplify each other or cancel each other out. This is constructive and destructive interference. This is the switch of the photonic world. By using heat or electric fields to slightly change the refractive index of the waveguide, we can steer, block, or modulate light at frequencies that make modern electronic processors look like they are standing still. The biggest driver for this technology isn't your desktop computer or your smartphone. It is the future of AI. Large language models and neural networks require trillions of calculations every second. Specifically, they require matrix vector multiplication. In a traditional CPU or GPU, this is done by moving numbers back and forth between memory and the logic units, creating a massive bottleneck called the von Neumann bottleneck. Photonic computing solves this in a way that feels like a cheat code. When you pass light through a series of optical modulators, the math happens instantly and natively. The physical interaction of the light waves themselves performs the multiplication and addition. This is called analog optical computing. Instead of converting a number into bits, doing the math, and converting it back, the light travels through the glass brain and the result emerges at the other end at the speed of light. The energy required to do this is orders of magnitude lower than what an H100 or a modern GPU consumes. We are talking about a future where a data center that currently consumes as much power as a small city could run on the energy of a few houses while performing 10 times the work. This is not just an incremental upgrade, it is a total reimagining of how computation happens.
If photonic computing is so superior, why isn't your laptop already using it? The answer lies in the difficulty of integration. We are currently in the hybrid era. Electrons are still very good at logic and memory storage, while photons are unparalleled at communication and specialized math. The biggest hurdle right now is the OEO conversion, the optical-electrical-optical transition. Every time we have to turn light back into electricity to store it in a standard RAM chip, we lose energy and introduce latency. Furthermore, there's the problem of the light source. To run an optical chip, you need a laser. Putting a laser on a silicon chip is notoriously difficult because silicon is an indirect bandgap material, meaning it doesn't emit light efficiently. Engineers have had to get creative, bonding exotic materials like indium phosphide onto silicon wafers to create microlasers. Then there's the issue of temperature sensitivity. Because light speed and refractive indices change with temperature, these chips have to be extremely stable. But these are engineering problems, not fundamental physics problems. They are being solved as we speak by companies and research labs across the globe. We are seeing the rise of chiplets, where an electronic compute die is surrounded by optical I/O dies, allowing the chips to talk to each other through light instead of electricity.
As we push deeper into the realm of light, we inevitably cross paths with quantum physics. Photonic computing is a natural bridge to quantum computing. While traditional computers use bits and photonic computers use light pulses, a quantum photonic computer uses single photons as qubits. Because photons are so stable and don't interact easily with their environment, they are the perfect candidates for quantum entanglement. They can maintain their quantum state across long distances without decohering. This means the glass brain we are building today is the infrastructure for the quantum internet of tomorrow. The same waveguides we are etching into silicon for AI acceleration will eventually carry entangled photons for quantum cryptography and distributed quantum sensing. We are building a platform that is future-proof. By trading electrons for light, we are moving away from the chaotic, heat-generating world of matter and into the precise, elegant world of energy. The transition from copper to light is not just a technical necessity, it is an inevitability of our hunger for data. We live in an era where the demand for computation is growing faster than our ability to provide it with traditional silicon. The heat wall was supposed to be the end of the road. Critics said that without Moore's law, progress would stall.
But they were only looking at one side of the equation. They forgot that we are not limited to the electron. When we look at a modern photonic integrated circuit, we are seeing the culmination of decades of research in semiconductor engineering, material science, and quantum physics. It is a masterpiece of human ingenuity. We are learning to weave light like thread, creating a tapestry of information that moves without heat, without friction, and without limits. The glass brain is not just a metaphor, it is the physical reality of the next generation of intelligence. In the early 20th century, we moved from mechanical gears to vacuum tubes. In the mid-20th century, we moved from vacuum tubes to transistors. Now, in the 21st century, we are moving from transistors to photons. Each leap required us to rethink what a computer is. We used to think of computers as machines that crunch numbers. In the optical age, we will think of them as crystals that refract information. The speed limit of electricity was never a dead end. It was a signpost pointing us toward the light. As we look toward the 2030s, the landscape of computing will be unrecognizable. Data centers will be silent, cool, and incredibly dense. AI will evolve from power-hungry clusters to lean, light-speed processors that can fit in the palm of your hand. The struggle against heat and resistance will be a memory of the past, a relic of the electronic age. We are finally shedding the weight of the electron. We are building a future that moves at 299,792,458 meters per second. This is the ultimate engineering achievement, turning the very fabric of the universe into the processor of our thoughts. There is no magic here. There is only the calculated, precise application of physics. We took the properties of light, the architecture of silicon, and the demands of artificial intelligence, and we fused them into a new kind of existence. The glass brain is here, and it is changing everything. As we continue to refine these optical chips, we are not just making computers faster, we are making them more aligned with the fundamental nature of information itself. Light is the fastest thing in the universe. It is only fitting that it becomes the foundation of our collective intelligence. The shift is happening now, in labs in Zurich, in clean rooms in Taiwan, and in the massive R&D hubs of Silicon Valley. The transition is underway. The first generation of optical interconnects is already shipping. The first photonic AI accelerators are being tested. We are witnessing the moment the lights come on in the machine. And once they are on, there is no going back to the dark, hot, and slow world of the electron. This is the era of the photon. This is the era of the glass brain. As we conclude this deep dive into the next phase of our technological evolution, remember that every limit we encounter is simply an invitation to look at the problem through a different lens. For decades, we looked through the lens of electricity. Now, we are looking through the lens of light, and the view is spectacular. The engineering challenges are vast, but the physical potential is infinite. We have traded the spark for the beam, the vibration for the wave, and the electron for the photon. The future of computing isn't just bright, it is made of light itself. Thank you for joining me on this journey through the waveguides and resonators of the near future. The world of semiconductor engineering is often hidden behind closed doors and microscopic scales, but its impact is what defines our civilization. As we push toward the next frontier, the principles of quantum physics and optical science will be our guides. The glass brain is no longer a dream, it is the blueprint of our future. And in that future, the only limit will be how much light we can trap and how far we can make it shine. Subscribe for more deep dives into the science of tomorrow. This was not magic.